There we go.
All right.
So let's read number one. I'll try one of these. I'll let you try one of these. We'll probably go back and forth to give you a chance to try some of the math, but this is factor label stuff, things you did last year, so hopefully it's not too bad. Number one, if I place 1.63 grams of potassium hydroxide in a flask, how many milliliters of 1.4 molar hydrobromic acid solution will it take to titrate or neutralize that base? So, from last year, if I want to solve an acid-base neutralization or a titration problem, and my end goal is to figure out milliliters of acid, what do I want to start my factor label problem with? If I want to solve for the acid, I should start my factor label problem with the base. Wherever you're trying to go or end up, you want to start your factor label problem with the opposite. Okay, so in this one, we want milliliters of acid. Let's start with the base. What do we know about the base? No, I'm saying like in the problem. What did they give me? I know I have 1.63 grams. I'm going to start right there. Now, eventually, I want to get to milliliters of acid. I'm going to need to do a whole lot of converting to end up over there. Okay? I'm at grams of base right now. What can I convert my grams of base into? Moles of base, always a good choice. We'll leave that for right now. We'll get that molar mass in just a bit. Let's set this thing up all the way, and then we'll start filling in some numbers. Moles of base to moles of what? Where am I going next? Yeah, okay, so last year when you did acid-base titration problems, factor label problems with neutralization, we always did like base to OH, OH to H, H to acid. I'm allowing you to bypass that nonsense because you're smarter. So you can go directly from your acid to your base or your base to your acid with moles. I'll allow it. But you do have to be on the lookout to make sure that it is a 1-to-1 ratio, right? I want to make sure that my acid provides 1 hydrogen ion and my base provides 1 hydroxide ion. If it's not 1-to-1, then my ratio must be something different. But you're smart enough to figure it out. We'll have a couple of those later today. I like your chances. So we're not going to do the base to OH, OH to H, H to H to acid thing. We're not going to write 3 factors that are 1-to-1 to 1 to 1 to 1 to 1. Sound good? We'll save you a couple steps. We're going to go from moles of base to moles of acid. And then the end goal is milliliters of acid, right? So now I'm at moles of acid. What can I convert my moles of acid into? Liters, because I have molarity, right? So that's where that number will go. I have moles of HBr, and we're going to turn that into liters of HBr. Now, I can totally write a factor going from liters to milliliters, but again, that's one of those things that I'm assuming you can just do in your head now. And if not, that's cool. You can write up the next factor. You're more than welcome to go from liters to milliliters. That's perfectly fine. But I'm going to stop right here. Let me fill in what I know. What's the molar mass of potassium hydroxide? I don't know. Time to look it up, right? I mean, I think I know. Hold on.
What's your guess?
It's 39 points off. I'm pretty sure it's 39. No, I'm sorry. That's potassium by itself. I'm thinking of sodium hydroxide. My bad. What is it? Bad T3. 56? 56.108. Second on that. Cool. That'll get us to moles of base. How many moles of base do I need for every mole of acid, or vice versa? 1-to-1, right? for every one of this base, I'll get a hydroxide. For every one of that acid, I'll get a hydrogen ion. And that's what I want. I want a perfect 1-to-1 ratio of neutralization. So we're good. Moles and liters of acid. That's molarity. I have 1.40 moles and 1 liter. I think this is my setup. Punch it all in. How many liters of acid do we get? And if you want to convert that right away, you're more than welcome to, because I did ask for milliliters, not liters. What do you get for a final answer? 20.8 milliliters?
Yeah.
So your calculator must have said 0.0208 when you solve for liters?
Yeah. 7.5.
Oh, sure. That's cool. 36 figs, right? The way to go.
Yep.
And that's it. That's what we're up to today. Now, I'm going to give you some more context. I'm going to kind of fill in some things that we didn't talk about much last year. But the math is factor labeled. Again, big takeaways are, if you want to solve for the acid, you start factor label problem with the base. You want to solve for something about the base, you start the factor label problem with the acid. When you get to the mole ratio of acid and base, just double check, make sure your H and your OH are perfectly equal. And if they're not, then you need a different ratio of 1-to-1. Okay? Now, on the right-hand side, I've got a graph. This graph is pH versus volume blank added. I'm going to write the word titrant. Okay? Titrant. Titrant. The titrant is whatever is being added from the burette. Okay? That is what I'm adding from the burette. It's called the titrant. What I'm adding it to is called the analyte. Fancy terms. I think I had the answer. Oh, I did have the answer back there. There you go. We're right. Good job, everybody. Okay. But long story short, this graph represents this problem. Okay. Early on, what did I have? I had nothing but pure base. So my pH would have started way up high by 14. And then I do a titration, or I'm adding acid to neutralize that base. So I add some acid, add some acid, add some acid, add some acid, and then eventually I reach what's known as the equivalence point. The equivalence point is right there. Okay? That is when I have equal moles of acid and base. Perfectly equal. So they perfectly neutralize each other. Okay? Because this is a strong base and a strong acid, when I have reached the equivalence point, or the neutralization point, I should have a pH of 7. I have equal moles of acid, equal moles of base. They completely neutralize each other. What do I have left over after an acid and base have completely neutralized each other? What do I have? This showed up yesterday's sheet too. What do you have after an acid and base neutralize each other completely? You got water and salt. What kind of salt if it's a strong acid, strong base? Neutral salt. pH is 7. So there's something else there. It's not just pure water, right? We've got some salt solution that was produced. But if it's a strong acid and a strong base that are reacting, it's water and neutral salt. So the pH is going to be 7. Okay? So we started with pure base. We added acid, and then we got to the equivalence point. That's the perfect neutralization point where acid and base are equal moles. They cancel each other out, and we have a pH of 7. If I just kept on adding more acid for the, I don't know for what reason, but just for fun, eventually I would end up with an extremely acidic pH, right? Close to 0, or even potentially less than 0, negative, if it's very concentrated. Okay? So that's the math. This is like the context. This is what's happening if we were to actually do this in a lab. And I ran this titration for real. Yes, Jagger?
So the graph is just there for like visual aid and help us find it has nothing to do with the math.
It'll come into play with the math in a little bit. Yes, as of right now, for this example, yes, it's just a visual showing what would happen if we actually titrated this in a chemistry lab. Cool.
With all other graphs, is it just a coincidence that like it's at the point of inflection?
No, not at all.
Or is it like
Yes, okay. So where this thing, again, you kind of see the shape is very S-shaped, right? This inflection point right there is always the equivalence point.
okay,
Always.
So like, if there was a graph, you could probably guess
Yes.
based on where the
What? Yes, and you should.
oh
Yep, and we'll talk about that too. All right. So if I have 25 milliliters of 0.8 molar acid in an Erlenmeyer flask, and it takes 18.32 milliliters of base, sodium hydroxide, to neutralize it, what's the molarity of the base from the burette? See what you can do. I know I've only shown you one, but this is last year's stuff. You had a problem like this, probably almost this exact problem with different numbers last year. It's been a while, but do some factor label, see if you can solve for the molarity of the base. I'll give you a head start. Feel free to talk to each other, and I'll pick it up in just a second. Go for it.
yeah.
Okay.
I like your rock. You're gonna take the black chair. Oh, can I take that?
I'm not using it.
Perfect.
Wait, he can't have the fan and the cool chair. Favoritism, favorite.
He did ask.
Would have said no.
That's who work. Actually, really nice. Like the first, it's the first time. Alright, what are we doing? NaOH, so we're gonna start with HCl. Oh. We had to do like 28 divided by. Oh. Is it 1-to-1?
Like
So you take that.
Wait, what?
Turn it into this is where you be turning into the same last year.
Plug it in like this.
Yeah. It's the same.
Oh, I did that.
Okay, so I'm at, I want 25 divided by that.
And this one, this is the step.
Yeah,
where we
but
like-
I knew that
divide my dad, my leaders of
Right?
not.
I mean, I'll see the offer.
Yeah. This time last year, we got about probably 13 inches of snow.
Once you grab 1.0.
Why did they request the thing?
No, they didn't. I did. Get a little more air moving. It just feels so stale in the building. I don't know. How we doing?
I got a number, but I don't think it's right.
I wouldn't be surprised if you're right.
It just doesn't make sense.
You just told me that the back box.
There it is.
No, but you should
Thanks.
Let's go.
All right. Nice. All right. So I'm asked to solve for the molarity of the base. So what do I want to start my factor label problem with?
Oh.
Acid. What do I know about the acid? I know that I have 25 mils and 0.8 molar. Which of those is a better unit to start our factor label problem with?
There's two fans.
Yeah.
Can I turn that one towards me?
I mean, I kind of turn it towards them.
It looks like it's facing out.
No, it's not facing the wall. We can all share the fans. If you're at home, it's really hot in the building today. I'm gonna start with the milliliters. Now, I can show my conversion from milliliters to liters. Okay, I can do that, but again, I think you know how. So I'm just gonna skip that part. I'm gonna go straight to liters because I know how to do that in my head. So I have this many liters of acid, and I'm going to convert that many liters of acid into moles of acid. And then I'm going to go from my moles of acid to moles of base. Again, this is the point last year where we would have gone from acid to H, H to OH, OH to base. We're skipping all that because we can do the ratio by just eyeballing it because we're smart enough. We're not going to screw it up. Right? So my base is sodium hydroxide. And then I'm going to go from moles of base to what? We're done, right?
Yeah.
That's all we need. Because what do we want? We want to get the molarity. What's molarity? Moles over liters. Hey, there's the liters part of the base. If we stop right here, we get the moles part of the base. And then we just combine those two pieces. So let's do that. This, going from liters of acid to moles of acid. I need a molarity. My molarity of the acid is 0.8. To go from moles of acid to moles of base, how many moles do I need of each to make that equal? Just one of each. That was a tough one. How many moles of base do I end up with? What'd you get? 0.0? That's it? It's an even number, really? Oh, I suppose. Okay. It's not gonna work. I kind of like those other boards, actually. Now I need molarity. What do? Take my moles, divided by my liters. How many liters of base do I have? I have 18.32 milliliters. Let me convert that in my head. And when I do that, my final answer should be, hopefully, 1.09 molar.
Yes.
Yes? And I'll label it appropriately with both a unit and what the heck it is. Molarity, sodium hydroxide. Okay? So here's another graph of this titration. What would have happened in the actual lab? In the actual lab, I would have started with nothing but pure strong acid. pH would have been really, really low, close to 0. I add base, I add more base, I add more base, I add more base, I add more base, and the pH is creeping up slowly but surely. And then we have this huge inflection where it completely jumps from like a pH of 3 to a pH of 10 in a matter of like a couple milliliters. And in the middle of that is what we call the equivalence point. The equivalence point, again, is equal moles, equal acid, equal base. And if it's a strong acid, strong base titration, or a strong acid, strong base neutralization, that should be a pH of 7. And it is. If for whatever reason I wanted to add more base, I could, and the pH would just end up plateauing somewhere up here near 13 or 14, because again, what am I adding? Strong base, right? So I have a very, very high pH if it's nothing but pure strong base, if I just keep going. Questions? All right, let's make it a little more interesting, I guess, but not really too different. An Erlenmeyer flask contains 0.2466 grams of solid acetic acid. I don't know what happened to my subscript here.
I like it.
You like it? I was underwhelmed. How many milliliters of 0.422 molar barium hydroxide are necessary to neutralize the acid? Go for it. Now, the difference with this one is it's a weak acid, strong base. What does it do to the math? Nothing. Conceptually, and in our graph, you can probably notice a difference already. But in terms of the math and the factor label stuff, it's the same. You'd solve it just like you did the other two. Go for it. Do some more factor label. And if you're feeling good and you're done with this one, go to the next one. I don't care. You can work ahead of me today.
What's the bonus? Who's done it already?
Okay, I got you there. Just that can't people.
What have you done yet? What's the bonus?
What
What is it?
I need water.
Did you like split a whole part of it?
If not, then I got it wrong.
Really?
60.
I guess I didn't think you were weird. Wait, so is it gonna take two of the hydrogen?
You're gonna take two of the base.
So just two of the others, right?
Yeah. Maybe 1/2. Yeah, it's like this first game. It's like the because like it's an acid, it's H plus ion. It's not gonna be. No. Yeah, because like if this were to dissociate, it would dissociate hydrogen.
Is it? You know that?
Yeah.
What is it? God, how did I do that?
All right. Wherever you're at, I'll start chipping away at this thing. The end goal is milliliters of base, right? What do I want to start my fact label problem with? Something acid. What do I have? What are my choices? I have grams. That's it. I guess that's what I'm starting with. So I have 0.2466 grams of acetic acid, HC2H3O2. I'm going to convert that from grams into moles, right? So I have grams of HC2H3O2 to moles of HC2H3O2. And we'll deal with that molar mass in a second. And then I'm going to go for moles of acid to moles of base. Base in this instance is barium hydroxide, BaOH2. I need one more step. It's getting kind of ugly. I'll just drop down again here. And I have moles of base. And I'm going to convert that to liters of base. Now I think I'm good. I wanted milliliters for my final answer. We'll convert the liters to milliliters in our head after the fact, right? Let's go like this. Okay, what's the molar mass of acetic acid? What'd you get? 60.0 what?
Yeah, that's what I got.
Everyone agreed?
Yeah.
Yeah.
Ratio. Acid to base. What do I need here?
Only two. Yeah.
My base provides 2 hydroxides. My acid provides 1 hydrogen ion.
Yeah.
I really want the H and the OH to be equal, right? That's what this is all about. So be careful. The base gives us 2 per molecule. The acid gives us 1 per molecule. I need twice as much acid to neutralize that base. Does that make sense? So our ratio is 1 to 2. Now at the bottom, I have my molarity of base. That's what I use. I have 0.422 for every 1 liter, and we're good. What'd you guys get? Yeah, since we're solving for liters, it's going to be 0.004 or something, right? What'd you get?
I said it.
What'd you get, Jack?
4.87. Yeah, look at the bottom. Yeah.
4.87 milliliters. So when you solve for liters, right, this is pre-converted. Be aware. My answer is not what our factor label problem really should be. It should be in liters if I'm solving it based upon what I've written. So when you punch it in, you're probably going to get 0.00487. And now we've changed that from liters to milliliters. So it's 4.87 milliliters of base. So I should probably write that down. Cool? Yes, sir.
Is this calculating the equivalent point?
Yes, it is.
So it's not neutral?
Correct.
It says 9 on the graph.
Yep.
But then the question says neutralize.
Yep.
So when you neutralize it, it's not neutral.
Yes.
Makes sense.
Well, I can make it make sense. So here's the deal. This is a weak acid, strong base titration. Do you remember from yesterday, right, when we were doing like mine tables and solving for the pH? Yesterday, I was having you solve for the pH of this equivalence point, whether you knew it or not. Okay? But if I have a weak acid, strong base titration, the pH of the equivalence point is going to be basic. And here's why. At this point right here, what I have is water and salt. But my salt is going to contain a basic anion. This is a weak acid. The salt that gets produced is going to contain C2H3O2, acetate. And acetate is a weak base because it's the conjugate base from this weak acid. So long story short, when I have a strong acid, strong base titration or reaction, the equivalence point is 7 because what I have at that spot is water and neutral salt. When I have a weak acid, strong base titration, my equivalence point is going to be basic. Why? Because I have water and a basic salt at that spot. Okay? Don't worry, we've got a whole lot more to talk about this. We're going to go much deeper in the next couple days. Hey, try one more, just for fun. We have now transitioned from a weak acid, strong base to a strong acid, weak base. More factor label, go for it. On this one? Yes.
Okay.
It will be 1-to-1.
Is this the one to one?
Isn't that weird? There's only one H.
The hard part is ammonia is our base.
Is that a one to one?
It is 1-to-1.
Did I do this wrong? Probably.
So I want to solve for molarity base. Yeah.
Okay.
Perfect. Okay. Everything's correct.
Which one is the
HNO3, we have NH3.
No, okay, so ammonia is one of these weird weak bases, right? Where when we put it in water, it produces hydroxide, but the formula itself doesn't actually contain
base?
Literally for our last step. It's basic term. That's like.
And it is.
It's like, you know, like the area of the areas.
Now, so many different.
Oh, sure. No, but like, people are not like that. Like, I've never thought about that. It's not hard. It's just like, Yeah.
Writing in math.
Yeah, it's not how I referenced some disclaimer, careful, teacher disclaimer, it says not how I taught you. If you get another question.
It's like, yeah, for us, it's not live.
Correct, yes, exactly.
I was like,
I was trying to tell one of you guys, it was, I could just disclose it, that's not how I taught you.
And with the.
Yeah, so I was like, I'll stick with calculus. But I'm still taking the AP test. I'm still taking the AP test. Oh, he's back. Yeah.
Yeah.
Well, I'm gonna learn the last semester. Like, all the course. I see the tree, that's it.
Yeah, but like also.
I'm sorry, what?
Yeah.
I'm sorry, Ben, what'd you say?
If someone shows up, let's say your class goes from like 1 to 155.
Yeah.
And someone shows up when it says 100, are they late?
Yes.
Yeah.
That's 1 o'clock, that's when the class starts.
Yeah, at 1 o'clock. At
Yeah,
1
so
o'clock.
they
is
got
their
there at 1.
Oh, me too.
No, that's in the first minute after 1 o'clock.
Yeah, but what second did he get there?
That's a good question. I don't know.
What
I'm not really a tardy kind of guy.
at 1 o'clock 0 seconds?
All right, what's the molarity of ammonia? Ammonia is a weak base. We want to start with the acid. What do I know? I know that I have 32.56 milliliters of 0.5 molar acid. Start with the volume. Do not start with molarity. That makes life much more difficult. I'm going to convert this in my head beforehand. Again, if you prefer to write out the conversion between milliliters and liters, no harm, no foul. Please do it if that's the way you feel comfortable. You're confident, whatever. You don't have to do this in your head just because I do it in my head. So I'm going to go from 0.03256 liters of acid. And I'm going to convert that into moles. And then I'm going to convert that from moles of acid to moles of base. And my base this time is ammonia. And then I want to end up with molarity, right? So I think I'm done. If I stop right here, I get moles of base. If I look back in the problem, they give me volume of base. Now it's milliliters, so we got to convert that to liters. But we can solve for molarity. Molarity is moles per liters. We got our two pieces. Let's plug in what we know. Molarity of acid is 0.5. Molarity of base, I'm sorry, this isn't a molarity of base, my bad. Ratio, 1 to 1. Now, this is non-traditional, right? That doesn't have hydroxide, like, in it, so to speak. But this is a base. Now, all of those weird nitrogenous bases, I'm using ammonia, so that's kind of nice, but I could have written, you know, CH3NH2 or CH32NH. They look fancier. They're harder to maybe pick out, but they're all behaving the same way. Okay? It's a 1-to-1 ratio. They're going to accept 1 hydrogen per molecule. So we've got what we need. How many moles of base do we end up with here? Did you do it?
No, just waiting for you to write this.
Excellent.
0.0. Yeah, that's what I got.
Yeah. Did you all say? 0.0163? Yes? Let's divide our moles by our liters. So my liters is 50 milliliters. I'm going to convert that in my head. And then overall, what do I get for molarity?
Ooh,
Now, if we look at the graph, again, this is a pH versus like milliliters of titrant added. Titrant's whatever's in the burette. In this instance, I'm adding, what am I adding, I guess? The acid? Okay. So I'm adding acid. I start with a weak base. pH is basic, but not obviously 13 or 14 like a strong base would have. The pH is 11-ish. I add acid, I add acid, I add acid. And then at this vertical spot, we have the equivalence point. The equivalence point is going to happen as central as we can get in that vertical region. Because this is a strong acid, weak base, titration, at the equivalence point, our pH is not 7. It's not neutral. And the reason is once we have equal moles of acid and equal moles of base, we have salt water. What kind of salt do we have in solution at our equivalence point? Not neutral indeed. It's an acidic salt. Hence why our equivalence point pH is less than 7. Now, where did that acidic salt come from? Well, it comes from the pieces of your acid and base. The salt in this instance would be ammonium nitrate. Ammonia, NH3, is a weak base. Ammonium coming from that weak base is in turn a weak acid. It's the weak conjugate acid of ammonia. Therefore, NH4 in our salt is acidic. And overall, we have a pH less than 7 once we've reached the equivalence point. Am I making sense? Kind of following me?
Yes,
Okay, let's talk a little bit more about this then. So all of the previous examples are acid-base reactions that are at the equivalence point. In other words, what you've solved for in those first 4 problems is the moles or milliliters or molarity required to reach equal moles, to reach the equivalence point. So let's define that. I've already said it like 4 times this class. What's the equivalence point? Moles are the same. In other words, moles of H1 plus equal moles of OH1 minus. Okay? Moles of acid equal moles of base. That is the equivalence point when I have equal of both acid and base. Another point of importance on a pH versus volume graph for a titration is called the halfway point. Don't hurt your brain cells on this one. The halfway point is halfway to the equivalence point. Equivalence, okay. That's true, there you go. I teach science, not English. Now, I can also describe this a different way. I can say this is the point where I have neutralized half of my starting acid or base. Same thing, right? Because when I reach the equivalence point, I've neutralized all of it. So the halfway point is when I've neutralized half of what I started with. Now, why does this point matter? Okay, there's a cool little thing, an equation that comes from this. It only works if we're analyzing a weak acid or weak base. So let me go to number 3. Here's the equivalence point. The halfway point is, halfway. Okay, that's the halfway point right there. Now, what happens at the halfway point is this. The pH of that spot equals the pKa. I haven't told you what pKa is just yet, but let's go to the next slide and we'll come back to this. What's unique about the halfway point is at this point on the graph, the pH recorded, and I think I just said this, is equal to the pKa of the weak acid. pKa is very closely related to pH. pH is the logarithmic value related to the molarity of the hydrogen ions. pKa is the logarithmic value related to the Ka of weak acids. In other words, if I want to solve for pKa, I take the negative log of Ka. What's K? It's the equilibrium constant. And if I have a little subscript A after it, what's that mean? And if it's a B, and if it's a W, water. And if it's an SP, KSP, solubility of a salt. And if it's a KP, pressure. Yeah.
For next year's kids, can you add a picture of Pikachu? Because it says Pika.
I will consider it.
Can you add it right in that empty spot down there?
Yeah, I will strongly consider.
Can you do it right now? No, please. I'm not kidding.
Yeah, I'll do it. I don't care. Sure.
Prove it right now.
No, I want to finish this sheet.
Afterwards, I want to see put it in.
Fine. Okay, so anything with a little lowercase p is the logarithmic power scale of that stuff, right? So when I have pH, it's the potential or power of hydrogen ions. When I have POH, it's the potential or power of hydroxide ions. If I have pKa, it's the same thing. Okay? It's just that we're putting our K values into a logarithmic scale. So here's what this does. At the halfway point, never mind. I thought I had on the next slide. But at the halfway point, pH equals pKa. That doesn't sound too fancy or too great just yet, but that's going to help us a ton when we start talking about buffers. Buffers. Okay. So at this spot right here, the pH at the halfway point of this graph equals the pKa. I can then take that pKa and change it and convert it into K. I can solve for the equilibrium constant by interpreting a titration graph.
That's crazy.
Okay, I don't know if that means a whole lot to you at the moment, but it's kind of a big deal and it helps a ton. And I'll tell you this too. I can all but guarantee that AP will have a multiple choice question where they want you to use the halfway point. And they're going to be like, hey, what's the pKa of this weak acid? And all they give you is a graph. And you have to realize that, okay, at the halfway point, pH equals the pKa. So I'm looking for the pH at the halfway point. Oh, it's like 4-ish. Sweet, my answer is 4. Okay? It's an easy question if you know that concept, but if you have no clue about that concept, then it becomes a whole world of, different struggles. Anyway, so let's go into one more example then. We'll deal with this equation, these equations, a little bit more later this week. And again, once we get into buffers, it'll make a bigger difference as well. But let's look at this really funky graph. Okay, there are weak acids that have more than one acidic hydrogen. What do I mean by that? Okay, I mean that an acid can be diprotic. A diprotic acid contributes 2 H1 pluses to this reaction, right? To the neutralization reaction. We also have triprotic acid. This is called phosphoric acid, H3PO4. If I want to neutralize phosphoric acid, I have to neutralize all 3 of those hydrogens. And the graph turns out kind of looking like this. It's like it's 3 titrations all in one. Okay? Let's kind of take a peek at this for just a second. So here's the starting spot. I haven't added any base just yet. I have nothing but pure phosphoric acid. The formula for that is H3PO4. I'm going to start neutralizing it. I'm going to start adding some base. And I'm going to add base and add base and add base. And then I hit this spot. You see how it goes really vertical right there?
Yeah.
This is what we call the first equivalence point. Okay, EQ number 1. Now, what does that mean? What that means is I have neutralized that first hydrogen off of my phosphoric acid. At this point in time, what I have predominantly is H2PO4, 1 minus. Because I've neutralized the first hydrogen. I add some more base. And I add some more base. And I reach this spot right here. That's the second equivalence point, EQ number 2. At that spot, I have now neutralized all of the second hydrogen. And the main chemical I have left is HPO4, 2 minus. And then if I keep on adding more base, I'm going to hit my third equivalence point, which is kind of way the heck up here, a little bit off the graph almost, because I need to get that vertical spot, right? This is the third equivalence point, EQ number 3. And at that spot, I have neutralized all 3 hydrogens off of my phosphoric acid. Okay? The reason why I'm showing you this is because it gets a little complicated when we have these diprotic, triprotic acids in play. This has 3 different equivalence points on the same graph. One representing neutralizing the first hydrogen, another representing the neutralization of the second and the third. This also has 3 halfway points. The first equivalence point happens from here to here. The halfway point is right there. That's halfway point number 1. The second equivalence happens from here to here. The second halfway point is in the middle. That's halfway point number 2. And then so on and so forth. I get to the third one. This is the third halfway point. That's an ugly number symbol. Eesh. I know. What does this mean? I have, at this point, pH equals pKa of the first hydrogen of that acid. At the second point, pH equals pKa of the second hydrogen of that acid. At the third halfway point, pH equals pKa of the third hydrogen of that acid. Phosphoric acid has 3 K values. Ka1, Ka2, Ka3. The first is for the first hydrogen, second's for the second, third's for the third. And in reality, if you have a solution of phosphoric acid, we have 3 equilibria all at the same time between all of the versions of that chemical formula. Now, how much of this do we need to know? Not a ton. Should you be aware of it? Yes. We'll talk more about these different pKa values when we get to buffers. But I think I'm good. I think I'll call it there for today. Thanks for your hard work. I appreciate it. People online, have a lovely, lovely afternoon. We'll catch you guys later.
Mr. Bronson,
Plenty of
at
time.
it right now.
Hold on.
Turn the screen back on.
Hey, 5 minutes.